Let's take a few minutes to discuss thiols and sulfides. A thiol is essentially the sulfur analog of an alcohol. So if we have this alcohol, we would call it 3-methyl-1-pentanol. We can compare that to this thiol, which would have the exact same name, 3-methyl-1-pentane thiol. So you see that instead of OL, we have thiol, and also the root name, or the parent name, keeps the E. We don't lose that. So those are the differences in naming thiols versus alcohols. Some interesting things about thiol. Methane thiol is in natural gas. And thiols come out of skunks when they get excited. So we've all probably smelled thiols before, and they really don't have a very nice smell to them. But that is some of the physical properties of thiols. So if we look at molecule NaSH, or sodium thiolate, this is essentially a source of SH-. This is a great nucleophile. Remember that atoms are better nucleophiles if they are larger. Sulfur is larger than oxygen because it's in the third row of the periodic table instead of the second. And so it has a larger reach, you could say, just like in the boxing ring. Somebody that's 6'5" is going to have a longer arm span or wingspan than somebody that's 5'0". And so the person that's taller is going to have more of an advantage in hitting the other guy. So the sulfur has a larger radius compared to oxygen. And so we can use SH- as a good nucleophile in SN2 reactions. And we've seen this in first semester organic, so I'm not going to get too much into that, but I just want to show you this example. This is a great, this should be an H, great SN2 reaction. You could even use it with secondary substrates, and you get primarily SN2. Not much elimination occurs here. SH- is just not a good base. We could also get two thiols to react with each other. And if we cook this up with sodium hydroxide, bromine, and water, we can produce what's called a disulfide. It's much easier to do this with SH functional groups rather than OH functional groups. So we can make a disulfide bond. You'll see this when you look up, when you learn about proteins. So I'm just going to mention here that proteins use disulfide bonds to hold themselves in a certain three-dimensional configuration. All right, so what is the mechanism of this reaction? Let me switch colors here and we'll get to it. So the SH has a pKa of around 10.5, so it's a reasonably good acid. So we can take, I'm going to draw the SH bond here, we can take our strong base, remove the H, and just like SH-, RS- is a great nucleophile as well. So we have a good nucleophile here that can react with bromine. Remember, we have molecular bromine here in our reaction. We can lose bromide and make an SBr bond. And now we've got a good leaving group on our sulfur. If I take another equivalent of the S-, right, because I made it up here, If I take another equivalent, you can see how I can form the SS bond through loss of bromide. So in the case here, we make Br minus, Br minus. We form the disulfide bond. So it requires just a proton transfer and then 2 nucleophilic attack steps to make this disulfide. We can also reduce disulfide bonds. Actually, what I should mention is that this is an oxidation. Remember that oxidation occurs when we lose hydrogens. That's one possibility. Here we've lost 2 hydrogens from our original thiols. And so this is an oxidation. We oxidize a thiol to a disulfide. We can also reduce reduce disulfides to thiols. So let's look at that. So anytime we've got an atom bound to itself via a single bond, we have a pretty weak bond. We see that with the OO bond. We're going to see that again with the SS bond. A mixture of HCl and zinc, as we've seen from other examples, is a good reducing agent here. And that's going to break apart this disulfide bond and give us 2 molecules of the thiol. So we can go backwards. And again, nature uses this when they're breaking apart disulfide bonds. Sometimes we need to break apart the 3-dimensional structure of a protein. We can reduce the disulfide bonds back to thiols. All right, let's talk about sulfides. So diethyl ether is the name of this molecule with an oxygen. Diethyl sulfide is the name of the molecule with a sulfur. And the synthesis of the diethyl sulfide is relatively straightforward, again using the rather high acidity of the SH and the great nucleophilicity of the S minus. So we can, I'm going to put a bond here again, deprotonate the hydrogen, creating the S minus. That can do an SN2 style attack on the ethyl bromide, losing bromide, and ending up with a new sulfur to carbon bond. And of course we've made NaBr. Br was our leaving group. We had Na from the beginning, the sodium hydroxide, and I've made a molecule of water in my first proton transfer step. These disulfides have interesting reactivity. You can actually methylate them, which you cannot with the oxygen equivalent. This puts a positive charge on the sulfur, and we have a bromide counterion here, but we can methylate that. Now, to an organic chemist, this is a powerful alkylating agent. We might use it in earlier chapters when we talked about SN2 type reactions. So, for example, if we had just a standard nucleophile, we could attack the methyl, release diethyl sulfide back to its neutral form, and have methylated whatever our nucleophile was. So this is a powerful alkylating agent. Nature has some of its own powerful alkylating agents. I'll list one of them here for you. S-adenosyl methionine, often abbreviated SAM, is nature's methylating agent. And I encourage you to look up SAM in the index of your Klein textbook and read a little bit about it. It's too big for me to draw here, but it is interesting from a biological standpoint. One last thing we can do with disulfides, with thioethers, also called sulfides, we can oxidize them. We cannot do this with a standard oxygen type ether. So if we use sodium periodate, we can put a double bond to the S. So this would be called diethyl sulfoxide. Sometimes also written like this. Resonance structure. We could also use 2 equivalents of hydrogen peroxide to essentially add 2 SO double bonds, and this is called a sulfone. So just some ways of oxidizing sulfides.